Hi, everyone. This is Dr. Griffith, ready to give you the lecture 1.5 on thermodynamics and energy flow. You may notice that I have my son's snake Sunset with me. I've been wanting to do a lecture with her for a while. I hope this doesn't freak anybody out. For me, I think snakes are super cool. And in fact, there's a bunch of food web stuff. So I'm going to try doing this because I've just wanted to for a while. Sometimes my dog Pippa's around. My dog Pippa is not around right now because she doesn't know we have a snake. I don't think that would be a good thing. Not food chain ready. So let's give this a try. Oh, sunset, don't put on that. All right, so let me tell you where we are in our notes, okay? So on page 17, energy flow and primary productivity, and we're gonna be doing 17, 18, 19, 20, and then finishing up on page 21. And yeah, look, see, there's snakes are tertiary consumers on page 20 there. All right, sunset, let's give this a shot. Okay, so our objectives are to explain how solar energy is acquired and transferred by living things, explain how energy flow and matter cycle through trophic levels, determine how energy decreases as it flows through ecosystems, and describe food chains and food webs and their constituent members by trophic level. So energy flow and dynamics, you can see here Batman and Robin are having a little conversation. You don't let in the cold, the heat goes out. So we're going to talk about the laws of thermodynamics here. So energy is the capacity to do work or to transfer heat. Kinetic energy is moving energy. So when you're actually going up the hill or coming down the hill. And then potential energy is stored energy. So I always talk about this with a rubber band. When you have that taut, that's potential energy. When you let it go, that is kinetic energy. So you're writing kinetic and potential down on your notes. So the first law of thermodynamics is that energy cannot be created or destroyed, but it can be changed from one form to another. So that's the first law. But you might wonder why I'm holding her for so long. Well, her cage is being cleaned, so I'm babysitting the snake while my son is cleaning her cage. All right, we'll see how long this lasts. The second law of thermodynamics that you're going to write down is increase in entropy. So energy always, the quality of the energy always decreases. So when energy changes form, it always degrades to a more dispersed form. So energy efficiency is how useful energy is accomplished before, how much useful energy is accomplished before it changes form to the next. So you can have very energy efficient appliances that make better use of the energy that's being put into them. So this is in short, and we'll talk about this more in person, but the reason for this is because the universe is expanding. Okay, so I'll talk about that a little bit more in person when you guys can ask me questions. So heat is the lowest form of energy, and then like solar radiation is one of the highest forms of energy that we use here on Earth. Entropy is also this idea that your room is messy because you haven't put energy in, but if you put energy in, it will go back to being organized again. So entropy is the reason that things kind of just keep falling apart, and that's because the universe is expanding. So there's different sources of energy and different sources of energy tasks. So as you can see down at the bottom, these are the temperature, the heat being released here, whereas up here, very high temperatures and high information, so high qualities of energy. So how do humans fit into this? So our enjoyment of life is a reduction of local entropy. That's kind of how you want to talk about it, okay? And it comes at the expense of polluting the environment because we're increasing the total global entropy. So no matter what, whenever things are changing, there's really no free lunch. We have to be expending energy. Okay, so the law of conservation of mass is that For any closed system, the mass must remain constant over time. So we're not consuming resources, we're borrowing them and transforming them. And so this is something that you can always think about within the ecosphere, is that everything inside our ecospheres is conserved. There's nothing going in and out except for the energy from the sun, right? It needs energy to keep going because of the laws of thermodynamics. So if you consider that all the carbon, all the hydrogen, all the nitrogen, everything just keeps cycling and changing form, it's a better way to think about the law of conservation of mass. So what's relevant to environmental science? It's pollution. And so that's what you're writing down on page 17. We'll always be faced with pollution of some sort, and what we want to do is try to reduce it. Okay, so let's get some more into these kinds of food web, food chain kinds of things. So because this energy transfer is always going to less order, you really, in order to feed things higher up on a biomass pyramid, which is what we're about to start talking about, you need to have the most things at the bottom of the pyramid. So 300 trout are needed to support one man for a year. The trout, in turn, must consume 90,000 frogs that must consume 27 million grasshoppers that live off of 1,000 tons of grass. So we're going to keep talking about things like this, and that's the kind of math that we'll do. So the highest level on our pyramid is a predator. So you got a cat looking for a mouse, a shark, or lions. Sunset is a predator. She likes to eat mice. You have omnivores that can eat both meat and vegetables. Consumers or heterotrophs, okay? And we're going to define these on the PowerPoint slides are not in order. Okay, so let's get back to this. So the predator, so predators only eat animals that it has killed. Okay, so you're trying to figure out where that goes on that list on page 18. So pause for a minute if you need that. Okay, omnivores can eat plants or animals. So pause for a minute and find that on your notes. And then, what's going on here? Sunset. Consumers, and let's say a primary consumer, consumers are heterotrophs, or organisms that can only obtain energy by eating other organisms. A decomposer is an organism that breaks down organic material into inorganic nutrients, just like we learned about in the ecosphere. Don't get caught on the back of the chair. Sunset, you don't go that way. Oh, there you go. Okay. All right, so decomposers break down organic into inorganic, and only bacteria and fungi belong to this group. Good thing she's not a constrictor, right? Okay, then producers or autotrophs are organisms that can produce their own energy through photosynthesis or chemosynthesis, but mostly photosynthesis. And then primary consumers are the things that eat plants. Primary consumers are on the second level of the food chain, and they only eat producers. Detrivores are things that break down organic organisms and feces into smaller organic molecules. And so these are earthworms and pill bugs and slugs. So detrivores don't break things down as thoroughly as decomposers do. And then good old carnivores, they only eat animals. They must be at least a secondary consumer. They only eat animals. So Sunset is a carnivore. She only eats animals. And at our house, she eats mice. Secondary consumers are third levels in a food chain, okay? Oh, So she's a carnivore and she's also a secondary consumer. All right. And the same for sea turtles and foxes. And you'll be able to see that sometimes an organism can be a primary consumer or a secondary consumer. It depends on what they eat. Okay, so there's some overlapping terms, right? So sea turtles are secondary consumers and heterotrophs and predators. Okay. Gorillas are omnivores, predators, and heterotrophs. And then a pill bug is a detrivore, consumer, and an omnivore. I don't know that I said, so what trophic level supports all other levels? That will be producers and autotrophs. Okay. So there's a little practice for you on the food chain. So you're going to complete the practice question in the packet. And remember, food chains or food webs, the arrows follow the flow of energy. So they always start at, say it for me, the sun. All right. So even if there's not a sun in there, I would draw it in anyway. So go ahead and do that practice on page 19. You can pause for a minute, or you can just go back and do that with the cat and the shrew and the robin and the wheat. Okay. And then we're going to talk about ecological pyramids. I just checked with my son. He said I could keep her for a little longer. So ecological pyramids, there's three main types of ecological pyramids. There's energy pyramids, also called trophic pyramids. Trophic means eating. There's biomass pyramids, how the mass of living things moves throughout a pyramid. And then there's a pyramid of numbers, and we're going to talk about that also. All right, so graphic models are the differences between trophic levels of a single ecosystem. All right, so you're going to write that down. Ecological pyramids are graphical models of differences between trophic levels in a single ecosystem. And the pyramid usually becomes narrower towards the top because that works for laws of conservation. So pyramids of energy, what you have to do with pyramids of energy is you have to use the 10% rule. So write 10% in that little star there over to the side. And it shows a flow of energy through trophic levels. 90% of the energy is lost at every transfer. So that's the 10% rule because only 10% is transferred. So the conversion of energy ratio of net is the ratio of net production at one level to the next. Pause it if you need to take more time. So in pyramids of energy, you definitely lose energy. And how do you lose it? So the remaining 90% of the energy that's transferred is lost through feces and urine. It's used in respiration, and it's lost as heat. Whoop. Stick with me, sunset. Okay. So pyramids of biomass. So biomass is the total mass of an organism. And the missing mass that becomes eaten, it becomes detritus and is decomposed. And then it's turned into the inorganic nutrients that the plant needs to build its structures and continue through photosynthesis. So here is some biomass pyramids. So you have, let's see, we don't have that one yet. Okay, so it's measured in weight per area, grams of biomass per square meter. So grams per meter squared. It's going to be like what a biomass pyramid is. And at the bottom, you have your producer, you have your primary consumer, your secondary consumer, and in this case, a tertiary consumer. So here's pyramid of numbers. And you have this in your, oh, just a minute. Well, that's the first time that happened to me. No joke. The snake pooped on me. Oh, so yeah, lost some of the biomass energy. No, really, I just had to like Oxy, clean the, oh, ugh. All right. Well, let's keep going. She's back in her cage now. So, I don't know. I keep going. Let's try. Whew. All right, so it's the number of individuals at each trophic level. So see, there's only 3 tertiary consumers, but there's 300,000 secondary consumers, right? And then the most producers. It has to be this way. Okay, so you have your pyramids of numbers in on page 20. Okay, and so you're supposed to say what the different pyramids show. So look at those and just kind of try to figure it out a little bit, and then I'll tell you what you should write down. Okay. So pyramid A shows a typical pyramid of numbers for a terrestrial system with many small producers, like a grassland. Pyramid B shows the effect of a single large producer, such as a tree. So one tree can provide enough energy for these other organisms. So pyramid of numbers can have it inverted like this, as with a parasitic food chain. So these are pyramids of numbers, how many there are at each one. So inverted pyramids with numbers, it can work. With biomass, it can work, but it can't work with energy. So inverted pyramids occur with both numbers and biomass. It occurs most often with numbers. But it can also result from seasonal fluctuations, weathers, and natural disasters. Okay, so can an energy pyramid ever be inverted? No. Like, how'd they even build that thing? So because the laws of thermodynamics, you've got to have the biggest at the bottom. Otherwise, it just breaks the law of thermodynamics. You can't break physical laws. All right, and so this is an activity that we will probably do in class as a group. And so we'll end there. I'm gonna keep cleaning up snake poop, and I hope you're having a wonderful day. Thanks for listening.